So in this example here, they want us to find the I core, right, and then the E core, given all these parameters, right, and some in the the parameter as well, right. But then before that, let's look at something, right. We said that when we do the Tafel extrapolation, right, something like this, we have anodic branch, cathodic branch, right, and then here's log, right, current density, and then here we have over potential, right. But there's a thing, there's a point where these two meet for the anodic and then the cathodic, right, and we are seeing that there's a particular potential that you can apply that will cause corrosion to happen in the system, right, which we call the equal, right. So there's the equal. So at this equal, right, which is basically a potential like similar to this, what happens is that we have a particular current density, right. So they're here because of the log, let's just do log I core, right. We are seeing that at this point here, there are you have the anodic potential current density being equal to the cathodic current density, right. Because at this equal, the quotient, the potential that will cause the quotient to occur in the system, right. These two are the same. This and this are the same, right? Okay. And then we know that these current densities, right, anodic and cathodic, we get them from the over potentials, right? Yeah. And then we know that over potential is let's see, is the difference between the applied potential. Let's make it this applied, and the let's see, let's make equilibrium potential, right. But then there's another thing, this equilibrium potential here can be the standard potential, especially when the system is in under standard conditions, right. So it can be, but it's not always standard, right. Yeah. So in order for us to find this, that's where if it is not under standard state, we use the next equation. But looking at what's happening here, this particular example is not under standard state, right. And it is not under standard state because even though the temperature is 298 Kelvin, the potential here is 2. It doesn't make the concentration of the hydrogen uh, 1, because we know that pH is equal to minus log of concentration of H plus, right. So if you try this, you see that the concentration of the H plus is not 1, so therefore not under standard conditions, right. So for us to be able to find this equilibrium uh, potential here, that's what we use in this equation, and we see that this right here, this equal here, is basically the standard, right, plus 0.059 on number of electrons, and then we have log, then we have oxidized form, and then we have reduced form, right. So this is how we go about this side, right. Yeah. So that would mean that before we able to find the I core, right, we will need to find before we need to find the I core, we will need to find this. We need to find something concerning to this. We need to find this, right. Yeah. And this applied potential here, right, because it's the applied one, is the equal that we have to apply for the correction to occur. So in this case, we are just saying that the equal is the same. And from this equation here, if this one is the equal, it's clear that this equal here is equal to the over potential, right, for any of them, right. And then we have plus over potential plus the equilibrium potential, right. So we are interested in this equation. So when we have this equal, we can equate it for the anodic and cathodic, right. So now we go on, right. So for the anodic, let's write the anodic at the top. So the anodic over potential, right. So basically the whole thing turns to anodic over potential plus the equilibrium potential for the anodic, right. So anodic, right, being equal to the potential for cathodic plus equilibrium potential for the cathodic, right. Before that, now let's try and find the what's the name, the equilibrium, right. So the equilibrium over potential for the equilibrium potential, not over potential, the equilibrium potential for the anodic is let's see, the standard, right. So the standard, so now we are starting anodic, so the standard has been given, which is this minus 0.25. So we have minus 0.25, right, and then we have plus 0.059. Number of electrons nickel is 2, right. So and then we have log, the reduced form is solid, so the concentration is 1, but then for the oxidized form, nickel, right, so the concentration over this, right, so nickel ions concentration of it is at 0.003, right. So we have 0.003, right. So that gives us the equilibrium potential for the anodic half, because it's not in the standard state. That's why we're using this equation. So here we have Nernst, equation, right? That's what we are doing here. All right, so what we get for this is minus, so let's see, minus 0.25, we have plus 0.059 on 2, then we have log base 10, and then we have 0.003. Right, so this gives us, for the anodic, we have minus 0.32, let's do 4 dp, 44 volt. Right, for the cathodic, since it's what do you call it, so equilibrium potential for the cathodic, since it's hydrogen electrode, it will be the same as this. We have E plus reduction, right, and then we have H2, so that will be, we know that to be 0.0, it's actually minus, we've seen that already, we're not going over it. That's minus 0.059, and the pH has been given already, right? So that will be minus 0.059, right? And then the pH is 2, right? pH is 2 times 2, so that gives us minus 0.118 volts. So now that we have this, we can go on and then equate the applied potential, which is the equal, right? See that the equal, the equal will be the same, right? That's what the potential we apply for them to corrode, right? So let's see. So that will mean that we can equate this for anodic and cathodic, right? So over potential, right? So let's see. So for the anodic over potential, and then plus this equilibrium for the anodic being equal to over potential cathodic. If you know what you are doing, just this one we're just writing this for us to see what we're actually doing, right? We are just repeating some things. So EQ for cathodic, right? We found these ones already. Okay, so what potential for anodic is let's see, that's B A, right? And then we have log, and then we have here, we are seeing that at E core, which is written here, the I cores are the same, right? Which is basically IAIC. So for the anodic it's IA, and we're going to replace it. Let's see. So at this point here, this is equal to this, which is the same as I core, right? Okay. So that I core is what we put here. So we have, let's change the color. So that's I core instead of IA, we just write I core because at that point it should be the same, right? And then we have I exchange current density, right? That's for this side. And then the equilibrium, we found that already for the anodic, that's minus 0, so this plus. So that's minus 0.3244, right? Yeah, and then equate it to that of the cathodic. So we have BC, Tafel constant, and then we have log, right? And then we have I core, right? Still I core again, and then we have I current density, right? And then we have we have, what's the name? Where is it? Yeah, so this is the next thing that we need, this. Yeah. So for the cathodic, right? And we have that to be this, which is minus 0.118, right? Okay. So then when we have this equation, we know that for the anodic, so for the anodic and cathodic, they are exchange current density the same, right? So it makes our work even way more easier, right? We can arrange all this and we will have something in this form, right? So using this equation, using this, right, and even considering how this one is, what we can do is we just do let's see, in fact you can just point this one directly if you give you what you're looking for, don't struggle. So let's see, so we have our BA was given us that's Tafel constant of anodic, that's 0.4, right? So let's see, 0.4 minutes, I'm just trying to check something. Yeah, so we have let's see, anodic, right? So we have 0.04, right? That's this. So now I'm punching it, so now we are working on this, right? And then we have log base 10, and then we have I core, let's make it X, and then we have this current density for the anodic, which is 10 to the power minus 6, right? And then now I'm adding this side, right? So that's minus 0.3244, right, being equal to, and I have BC. BC was given as minus 0.13, right? Now I'm here. So equal to, now I'm here. I have my log. We have the log. And you have this I core again. Let's keep it X. And here we have a current density, which is 10 to the power minus 6, right, for the cathodic. Minus 6. Let's see if we did. Yeah. Right. So this, right. Okay. And now we move on to this side, which is minus 0 0.118. So now let's see if we get for the X, which is the I core we are looking for. Right. So the I core that we are looking for is basically this. So we end up getting I core, right, to be, let's see what the calculator is giving us. 0 0.01234. 1, 2, 3, 4. Right, so 1, 2, 3, 4. Oh, let's move it down so we can fit it there. Okay, 1, 2, 3, 4. And we have 1, 6, 3, 7, 2, 6. So when we change it to scientific form, let's see what we have. Calculator can do it straightforward, but this one I don't know how to do it. That's why I'm going this way. 1, 2, 3, 4, 5. Right, so here I end up with 1.637, let's see, 3, right, times 10 to the power minus 5, right, that's my core, minus, very important, minus 5. So it's a current density, right, so which is amperes per, let's see what we have for the current density, right. So it was in both was amperes per centimeter square, so this should be the same, right. So amperes per centimeter square, right. So this is what we'll be having for the I core, right. For the I core, this is what we have it, right. So let's see. And then the next thing was for us to find the E core, right. So let's see, which is the potential that will apply that will cause corrosion to occur, which we've seen to be this right here, right. So just the potential, any of them, whether for the anodic or cathodic, right. Right. So that's what we're going to do next. So let's see. So we have this. So just copy it. Okay. So we are just going to use the anodic, right. I'm just going to use anodic. Just going to use anodic. Okay. So let's see. We're just going to use anodic. Let's change this one just so it's clear which one we're trying to find. So E core, right. So we have the, let's see, we can get the over potential, and then we have the equivalent. So let's use the anodic, right. So the E core that we are looking for will be equal to the over potential. So now if we are using anodic, then we're using this, the equilibrium potential for the anodic as well, right. So let's see. So here, let's clean this up. So here we have a Tafel constant, and we have log, right, and then we have a I core, right, which is the same as the IA, right. Yeah, at that point, at the E core, right, when we refer to this diagram we have here, we know what's happening, right. Yeah, so we have that, and then we have the exchange current density, this, and then we have equilibrium for the anodic. That's anodic is minus 0.3244, right. So that's minus 0.3244. So let's see what we have for the B. Tafel constant for the anodic is 0.04, right. And then we have log is 10 here. Corrosion density, yeah, corrosion current density, that's 1.6, right. 373 times 10 to the power minus 5, right. And then this we have 10 to the power minus 6, right. Minus 6. Yeah, so that's it for this side. So we punched all these, on this. Now we are done with this one, right. So we have a plus, which basically we have a minus 2, so we have 0.3244, right? And that gives us the equal, right? So we end up getting our equal to be minus 0.275 for the V8, and that will be in volts, right? Yeah, so that'll be in volts. So this is the equal and I equal, and that's it for this particular example. All right.